Welcome back to The Explainer. So I want you to picture something for a second. Imagine you're building a highly complex machine, right? You wire it up, power it on, and you know exactly what you designed it to do. But then, as you pump more power into it, it suddenly starts performing tasks you literally never programmed it for. Tasks it realistically shouldn't know how to do at all. Now, I know that sounds like pure science fiction, maybe even a little creepy, but this isn't fiction. This is exactly what happened during the development of large language models like GPT-3. Today, we're diving into a deeply unsettling scientific mystery right at the frontier of AI, the sudden emergence of capabilities that absolutely nobody designed.
To guide us, today's explainer is heavily grounded in this fantastic, deep dive investigation written by Aaron Rose for Tech Reader magazine. It's just a profound look back at the history of GPT-3, and specifically that chilling moment when researchers realized their creations were, well, kind of acting on their own. Ultimately, it's a story about scale, observation, and really the limits of our own human understanding when we're faced with this kind of rapid technological acceleration.
To really grasp why these researchers were so uneasy, you kind of have to imagine the charts they were staring at. They'd test these models for new capabilities as they got bigger, but the performance graph wouldn't show, a nice, steady, predictable climb. Instead, the line was just completely flat. Nothing, nothing, nothing. And then, abruptly, a sharp vertical rise. Then something. The capability didn't evolve slowly, it just appeared out of nowhere.
Let's break this down in Section 1, the capabilities nobody designed.
Okay, so this whole phenomenon completely shatters our traditional mental models of software. Normally, if an app has a feature, it's there because a human being put it there. Someone made a decision, they wrote the code, there was a pull request, they chose to build it, so they built it. But these emergent abilities in language models, they had absolutely none of that provenance. Nobody wrote a function for these new skills. They simply popped into existence because the model had been made larger and trained on more data. And honestly, for a while, that was the only explanation the scientists had.
And we aren't just talking about minor, quirky little glitches here. We are talking about the models suddenly writing syntactically valid code in programming languages they weren't explicitly taught. We're talking multi-step arithmetic, flawless translations of rare languages. They could follow really complex conversational instructions perfectly, despite completely lacking explicit programming for it. The researchers set out to build a next token predictor, but they somehow ended up with something that acts incredibly like a general reasoner.
Now, this kind of situation, where the engineering completely outruns the theory, it isn't totally unprecedented. Think back to the Industrial Revolution, right? People built fully working steam engines way before thermodynamics even existed as a formal scientific discipline. Or the Wright brothers. They certainly didn't wait for a complete mathematical model of aerodynamics before taking flight at Kitty Hawk. The engines worked first, the theory explaining exactly why they worked came later. And with large language models, it's the exact same story. The empirical observations outran the theory. The engineering simply arrived before the explanation. Moving right along to Section 2. Nothing, then suddenly something.
So you're probably wondering, when exactly does the spooky phenomenon kick in? Well, the magic threshold seems to be roughly 100 billion parameters. That was the massive, distinct line in the sand where researchers consistently watched these emergent abilities just abruptly switch on. Below that massive scale, the models were clueless at these complex tasks. But the moment they hit that scale and beyond, they suddenly had it figured out.
Which brings us to Section 3, the phase transition.
To try and make sense of this deeply abstract concept, researchers actually borrowed a concept from physics. Think about freezing water. At 33 degrees Fahrenheit, water is a liquid. Drop it just 1 degree to 32, and boom, it's solid ice. Now, the underlying molecular motion is changing continuously the whole time it cools down. There's no break in the actual physics. But the macroscopic behavior undergoes a total, complete transformation at one very precise threshold. That is a phase transition. And researchers realized the model's loss curves were dropping continuously, exactly like the temperature dropping. But the observable behaviors, the actual capabilities, were jumping discretely, exactly like water suddenly becoming ice. Or, here's another way to think about it that might hit a little closer to home. Think about a little kid learning to read. For months, a parent might see absolutely zero visible progress. The letters and sounds just seem like arbitrary squiggles. But invisibly, thousands of tiny little adjustments are accumulating in the child's neural architecture. Those patterns are consolidating in the background. Then one day, they just read a whole paragraph. The capability arrives fully formed, almost like a switch was flipped. The model's training process is doing something structurally very similar. Continuous, invisible improvements happen behind the scenes, eventually crossing a threshold of actual use, and sudden, visible capability emerges.
All right, let's flip the coin and look at Section 4, the measurement debate.
Because, good science demands a healthy dose of skepticism. And around 2023, skeptics raised a core question that was just brilliant in its simplicity. Were these crazy emergent abilities a genuine, real property of the models themselves, or were they just a trick of our testing instruments? Was all of this just an artifact of how we were measuring them?
To really get what the skeptics were arguing, you have to look at how these benchmarks usually work. Most of these capability tests are strictly pass or fail. So if a model's internal accuracy moves from, say, 49% to 51%, the test just flips from total failure to total success overnight. To the test, it looks like a brand new capability appeared instantly out of thin air. But to the model, it was just one more tiny continuous step forward. When researchers started using tests that gave partial credit, that spooky, sharp vertical rise, it actually flattened out into a much smoother curve. So some of that initial spookiness definitely diminished.
But here's the thing, and this is absolutely crucial. That debate, while totally valid, doesn't really change the practical reality on the ground. Because even with better measurements, some behaviors still remained genuinely abrupt. And more importantly, before GPT-3, the dominant expectation in the field was that scaling would eventually hit a ceiling. Everyone thought just making models larger would eventually stop yielding better results. But the empirical evidence proved them wrong. The capabilities just kept unlocking. Those ceilings that the experts so confidently predicted, they just kept not appearing.
Which naturally leads us into Section 5, why this changes everything. This is where the real-world stakes get, frankly, a little intense. Aaron Rose sums this up perfectly in the source investigation. He points out that we are so used to software being intentional. We build a specific tool to do a specific job. But emergent abilities, they completely break that chain of intentionality. We're now building these massive, opaque systems where we literally do not know their full capability space in advance. We only discover what they can do by training them, throwing more compute at them, and basically just watching what happens. If that doesn't give you a deep sense of intellectual humility, I don't know what will.
So, the really urgent takeaway is this. How on earth do you ensure a system is safe when you don't even know everything it's capable of doing? That right there is the absolute core of the alignment problem. It is fundamentally incredibly difficult to align a machine to human values and safety constraints when the very process of making it smarter, literally just feeding it more data and running the algorithms, produces skills that nobody ever designed.
And that leaves us with a provocative, almost haunting question to chew on as we wrap up today's explainer. The engineers built the infrastructure, they scaled up the models, and these systems just started doing things nobody asked them to do. So how exactly do we control a system that might invent completely unpredicted, totally new capabilities the very next time we cross a threshold of scale? Understanding the pure mathematics behind why this happens is really the only way forward, and that sets the stage perfectly for part 4 of this series. Thank you so much for joining me on this deep dive. Keep questioning, keep learning, and I'll catch you in the next explainer.